Everybody, thanks for coming by for a kind of distributed computing 101. So we'll try to stick with the 101 session-like. I'm not guarantee that it's going to stick all the time with the 101, but we will try still. So the main title is how to use Spark for this kind of distributed machine learning or computing in general. And for that, since using Spark can be quite a long process before you can deploy a job, we're going to use the browser that allows us to be more interactive in a way that we are structuring on models. So the main outline today, so we will cover what is machine learning, try to scope what is exactly, for us at least, machine learning, how it can be used, when it can be used, what we have to clear out before using it efficiently in a production environment. After that, how it can be used using the Apache Spark. Finally, how to apply machine learning models already prepared or available in the MLlib library, which is part of the Spark ecosystem. And finally, what we think that will be the future or part of the future in machine learning in general. So we are Andy Pertella and Xavier Tordoir. So I'm mainly a mathematician, but I only end up doing real math since last 2 years, because before I was mainly a computer scientist, because math wasn't that understood before. And finally, big data came out, and they were all interested in having a data science included into their platform. So that's why I, for a long time, developed in Scala. I picked up Apache Spark, and I'm also a trainer for TypeSafe and other companies in this environment.
Yeah, on my side, I have a background in physics, and I've done quite a lot of bioinformatics in academia. I've also done some machine learning, trading models for the financial market. That's where I learned what is overfitting the hard way. And then I worked with, HPC, and then out of this frustration, I'm now happy working with Scala and Spark. So there's a kind of new job that arose a couple of years ago, that is that data scientist. And I think that, machine learning is really about science with data. And when you think of science, a scientific attitude means that you want to have a model of the universe, or at least part of it. And you have to be honest with your model, and you have to admit that some circumstances might prove that your theory is wrong. And that's really the point that we'll insist on today, is that you have to be really careful with the way you validate your models before they go into predicting things, because there might be a loss that is more than just a loss function that we will see later, but it can be a heavy loss if you're working with healthcare and things like that. So someone is responsible for the mistakes. Don't forget that. So machine learning is in some way opposed to what you do usually when you do physics. That means that you want to test a theory that is an abstraction out of mathematics. And you use the data to see if this abstraction is correct in some way. With machine learning, you get rid of this first principle, this law of physics, or the way things would interact together, because maybe you don't know how they would interact, or the system is simply too complex to be tackled that way. It means that you really want to model the world only from the data, and you want to find out what are the dependencies in the variables you observe only from the data. This implies actually that when you're dealing with a problem, the machine learning part is actually a small part of it. You need a lot of things around that. That means, what are you exactly trying to understand in the world? What are your hypotheses? What is the way you collected the data? What kind of transformation you made out of that? How will you interpret the model that results from your machine learning? And all these requires quite a lot of expertise in the domain. And this is not what this talk is about today. It's a lot of things around that. We'll focus on the technical part here of really modeling the machine learning part. And the machine learning part means that you have an engine, a learning machine, which is something that is actually implementing a set of functions, and you want to find out from these functions which one is the best to describe the relationship between your variables. So what is machine learning really? You have something that generates samples, that is all your set of variables, and this is the input of a system that creates, where's the pointer? Okay, no pointer. So, from your input, it might go into a system that creates an output that is completely deterministic from the X and something that is unknown, that is usually the noise. And the learning machine actually will try to figure out which function is the best to describe the relationship between your input and your output, and having an approximation of this. And how you do that from a mathematical perspective is that you really have to minimize a risk function. And this actually, in computing terms, is a sum, so don't worry about this. And you need a loss function that describes the way you think the error should be modeled when you have such a model. So for example, if you want to do regression, it means that you're actually observing an output that is a continuous value, and it depends on a set of variables. The loss function is simply the sum of the square or difference between the real outputs and the predicted outputs. And you have, for classification, a loss function that tells you how likely is it that, or probable is it that you are wrong in classifying your items. And then you have the problem of clustering. In that case, you have a data set and you want to try to find out groups of data that are related in some way, so you don't have an output. That is what is called unsupervised learning, which means that you don't have an output that you want to compare your model to. You want to find a model that is able to describe the data. For example, when you do clustering with k-means, you're trying to find out points that are representative of group of points. So that means that you are actually trying to find out functions that map a point from your input into one of these cluster center. And the function you want to minimize, the one that represents the loss, is actually the distance between a point and its projection on the cluster center. And you have the same kind of formalism if you want to do density estimation, which is another case where you don't have an output. You're just trying to see what is the shape of your overall distribution. Okay? I think I've done enough with the theory. And as Andy mentioned, we work with the notebook. And let's run some machine learning on this one. Okay. So the idea with the Spark notebook is that it's an interactive interface on a distributed system. And specifically, it's Spark here. Yeah. Yeah, so it's trying to load.
My graphic card is lagging.
So the advantage when you work with this system, if you've been working with notebooks, I guess, the interest here is that you have a gateway to any kind of resource you want. You can work it locally, and usually we develop our machine learning or Spark jobs actually in the notebook in local, and then we can try this on a cluster when we start paying money before it goes into a production mode and it's deployed as a complete job. So the principle here is that we just execute some cells in which we edit code in our favorite language, which is Scala. So we import here some stuff because we will actually generate some data. And the data we will generate is values from a space which is from 0 to 1, from a uniform distribution. So we take x values, and the response from this x will be a function which is x squared plus some noise. Okay? We have to wait for
the kernel to start.
The kernel to start, as mentioned.
Yeah, that's a good part with live demo, of course.
Okay. So actually, in that way, we are cheating because we know the way the data is generated. But what we will show you is that when you apply machine learning on this data set, even though you know what function you should expect, the best function to fit the data may not be that very function. And that relates to what is validation of your model.
It's coming along. Keep on.
Maybe we can scroll.
Yeah, sure.
So we'll execute that later. But the generator of X is a uniform distribution. So we have data along the X-axis which are uniform. Then from this data, we take the square, and then we take noise that is taken from a normal distribution. You'll see in a second what this data look like. And then we will assume that we generate a lot of this data, 1,000, and this represents the universe. All the data that is available for this generation model. And then in reality, what you usually have as an analyst is a fraction of the world. You cannot have all the data about everything, okay? So you only have a small fraction. And what you want to do is to try to have a model of the entire universe just from a small part of it. Okay. So once we have created 1,000 of these samples, what we do here in this, yes, okay, so that is one data set. So you see you have values on the y-axis that are growing with quite a lot of noise, and you have a uniform distribution on the x-axis, okay. So what we do here, it's interesting because it's Spark. I don't know who is familiar with Spark, has used it, well, a few, but not that many. So it's important to say that, so the Spark context is the gateway from is the API that gives you the gateway to the distributed computing system. So for example, it provides you the read functions to the distributed data set. And the very important notion that is also available in Spark is the RDD, Resilient Distributed Dataset. It's an abstraction that allows you to define transformation you want to do on this distributed dataset in a lazy way. So it allows you to define a series of transformations you want to do on your dataset, and then it allows you also to trigger those computations when you call an action, for example, when you want to count items in a distributed data set after making transformation. It's the count that triggers the series of computation on the data set, and then you, of course, you need to read the data to know how much data you have in the system. So what we did here is that we created locally a data set, and then we ship it to the Spark context as a distributed data set, but in reality, if you work with real data, the data is distributed and you just call a read function on that distributed data set. So where we are. So here we have functions that actually allow to take this data that we created and to transform them into a data set. So we actually format the data for the machine learning library. And what this says we have actually 4 models that we will try. The first model is simply a constant. We'll try to find the average of a data set. The second one is a constant plus x, which means that it's a straight line that is trying to fit the model. The third one has a second order parameter, so it's curved, it's a parabola. And the third one, the fourth one in the middle. The fourth one is a third order function. Okay, so we have 4 models and they increase in complexity. Okay, so let's see what a sample looks like.
So, yeah, browser lagging.
Yeah, the browser is lagging. Yeah.
Which one? This one?
Yeah, just one. So that is a simple sample. It takes only 1% of the entire universe, so you have about 10 items, and you see they're growing. Now let's do the fitting. Okay, go down. So we import the MLlib classes that allow us to do this linear regression model. So it's just linear regression. Okay, you may have an x square on an x to the third power, but it's a linear problem because the parameters are linear with the different features. Okay, and the important function here is that we are training this on the least square problem, which is the typical linear regression, and the algorithm LBFGS is actually the one we chose because it has a quite fast convergence. So it's better to use that one in a demo. Okay. Okay, you can go down. Those ones don't need to be executed.
Anyway.
Okay.
I can go there.
Okay, so here we define a function that will measure the mean square error. The mean square error means that, okay, you have a model, and that model is able to make predictions, and if you want to see if those predictions are good or not, you need to sum the difference between the prediction and the actual value. You take the square of this, and you take the average. Okay, it's a measure of distance between the model and the reality. Okay, and as I said, what we do here is that we will run 25 times the following procedure. We take a small sample of the universe, which is what happens in reality for any data analyst in the world. Okay? And we will train every 4 model on this and measure what is the error on the entire universe. So we will really measure how good the model is for the entire universe, given that we are only taken a small sample. And we'll also measure the error on the training set to understand the dynamics of training.
It's still running, but I could try to show it.
So interesting, when you're working with Spark, of course, you're working with a distributed environment, which is always a bit tricky to grasp what happens there. And Spark provides actually a UI which gives you a view of all the tasks that are scheduled, the time they took to execute, the memory they used. And you see here that we're making quite a number of simulations. And the core part is to train the model. And training the model consists actually in taking the data, making some computation to compute a model, which is only, in the worst case, 4 parameters. And it's an iterative process. So read the data again, update the parameters. Read the data again, update the parameters. And that's what Spark is good at. It's such iterative processes because it has mechanisms that allow to cache the data in memory as much as possible. Okay.
And just to show that there are 2 tasks running in parallel, there are 2 stages per job. And there are now around 400 jobs that run. So it's quite a lot of computation, even though in Scala it represents 2 lines of code, of course. in Scala. Okay. So it will keep on computing.
The next step will consist in, we have 25 experiments in some way, and we will aggregate this data, counting the number of times the model of order 0, 1, 2, and 3 was the best one. One would expect that the best model is the one of order 2, right? Because it's the generative process. We'll see that it's not necessarily the case.
Where are we? Yeah, my graphic card is taking the whole charge. My browser is even slow.
Okay. So you can enjoy this nice fold left.
We can also write case classes.
Yeah.
Okay. Right, so we are reaching the end, I think. More or less. But maybe I can continue on the rest. Oh, you can go on. You can go on a bit, and then we will get back to that. Let me just go there. My browser is really lagging. You can continue on. I will show them.
So what we will see actually is that even though we know the generative process, the best function that fits the data is not that one. And there's a reason for that, is that we've taken a really small sample. So we don't have enough data to represent correctly the universe with the generative function. Because we have so few data, we have what is called overfitting. So the model has too much complexity, so it's actually fitting the noise that is very specific to that sample I've taken. And that's why this model is not as good as the one I would have if I had taken a larger sample. Okay? So the trick here, when you run the system with many simulation, you see that if you take the average of this, you're able to grasp which model should be taken, which version of the model should be taken. And this leads to really the very fundamental point of machine learning, which is validating your model with procedure like cross-validation. So you train your model on part of the data, and you test whether this model is correct on another set. And you may have to do that quite a number of times to be able to find which model is the best one to represent the universe given the data.
We'll show the result after. Actually, my video card is taking the whole charge. I don't know why. So, yeah, like Xavier explained, in this example, we took very small samples in the whole universe. And the thing is, how we are optimizing the functions is by adding component to the function, the model, let's say. That means that we can have a model that is constant, linear, squared, and on the trained data, it's going to take all the time the last one, F2, because it has the higher number of parameters to tune. However, when you train it, when you apply your model that you have trained on a small data set, that was quite good with relatively to the real universe, which is squared. When we apply it on the whole universe, finally it will pick up the order 1 function. That means that if you would have stick with the F2, order 2 function, you would have your prediction would have been less important or accurate than with the order 1. Because even though you have an order 2, the shape of the function is not exactly the same that the universe is actually containing. So the idea is finally to, rather than picking a few examples or trying to have a few examples of the universe, the idea is to run a lot of those samples in parallel, if possible. That means that you try to cover as much as possible from the universe. Okay? So what you're going to do is you are going to increase your variance, finally. But still, if you have a model of order 3, it's going to pick in the training set the order 3 function. Okay, so if you are happy with the training set, that means that you are going to use all the time a model of the order 3, which is more hard to interpret finally than the order 2, although the universe is an order 2-1. So you are overfitting the data set. That's why you always have to cross-validate your functions with the whole universe in this case. And is going to, since we have more data, the universe will dictate the model selection to pick finally the one which is nearer from the real life, from the real world. And so this is for many samples, but the other idea that you can achieve with the great technologies that we have right now is that we can take bigger samples. That means that each sample will have more variance than the smaller ones. And you can take bigger samples and still run them in parallel. But still, if you run your model selections, your different models, you're going to pick the F3 on the training data set, which is not the one that you would like to have, but by running on the training set, on the whole universe, the right model is F2. So we took more small data sets, we increased the data size, and finally we had the right function when we applied it on our cross data sets, or cross-validation data sets. And if we push this idea way further, we reach we can use a k-fold. And k-fold means what? You take the whole universe, you split it into different parts, it's partition finally. And what you're going to do, you are going to run your algorithms on the universe minus one part. Then you run it on the universe minus another part and you re-add the previous one. So it's always n minus one parts. But that means that you will always tune your algorithm on a different training data set. Because if you constantly reuse the same training data set and test data sets to validate your function, that means that the test data sets becomes part of the training data sets, right? So that's why bigger samples and k-fold can reach better performances. And pushing it very further down to the number of items that you would like in a partition, you reach the jackknife one where you only remove one point of the training samples. So that leads to the fact that we really need frameworks that allows us to run a lot of models or to run the same model on a bigger data sets. Okay? And that's, in a sense, what is Apache Spark. Can you take over?
Okay. Maybe I just show you the promised result in some way. Executed that. Okay. So here we have a small table. You have the order of the model, and we counted the number of times each model was picked as the best one, and you see that it's the order one that is the best. If you look only at the training set, you get the one with the largest complexity every time. Okay. If we run the same thing, taking a larger sample, we would have found out that the second one was the best. Okay. So this is the illustration of validating your model in a clever way. Okay. So what we do a lot is working with genomics data. As Andy said, it's really interesting data sets because they're quite big and there are quite some constraints. So not everyone is familiar with the data. So in a nutshell, the nature of the data is that actually your samples are people. Okay, so each item you have in your database comes from an individual or from a living entity, let's say. And the feature associated to these samples are the genotypes. And the genotypes actually is something that points to a location in the genome. So a position on a chromosome. A chromosome is just a string, let's say, so it has a metric. We can measure a distance to a point on the chromosome. And on this position of a chromosome, you might have a mutation that is present or not in the individual, and the data is actually this. is there this mutation at this position of the chromosome on this individual. The trick is that we have 2 chromosomes of each kind, so we have actually 2 values to gather at this position. We take the data from a public database, which is 1,000 genome, and the principle is that samples were taken from different populations in the world, were completely sequenced, and we have the genotype for all these individuals, and this serves the scientific community to understand better our genomes. And what is this data? Actually, it's only 1,000 samples, which is very, very few. And this implies that if you want to do some analytics on so few samples, you need really to be careful. You need good machine learning skills to do that. Second thing is that because you have so many features, we're talking about 30 million genotypes per individual, it means that still it's a lot of data, okay? And in a couple of years, we'll have millions of such samples, and it will grow to tens and hundreds of millions of such data in the near future, okay?
So, yeah, based on the data that we have right there, so in a sense, we have a lot of data, 1,000, let's say, it's a lot in genomics. But those data are more or less classified with the population, geographically positioned. So we had this idea, the second time that we have it, to try to use the data in order to detect how this population is distributed. But not only a genomes can be attributed to one population. It could be attributed to several populations. Why? Because we have parents that might come from different parts of the world, but we are inheriting these genes from them. That means that our genomes could be, in a certain portion or probability, be classified as a different topic. So we had this idea to run a latent Dirichlet allocation for that. So what is that? A latent Dirichlet allocation is able to constrict or to separate topics in documents. Okay, so we have documents, and you can separate topics. You ask for 20, you try to find the 20 topics in it. But it will use for that the probability that one word is part of all of those topics, and the word is the component of the document. Here, a genome is what? It's a document. A position in the genomes is a word, right? So we will try to find where the genotypes is most probable to which population these genotypes could land in. So we run it. We can show really quickly the notebooks if we like, but the thing is that although we could run the algorithm, we could find a good probability set for all the topics, for all each genomes, we hadn't the predict function. So it wasn't yet implemented. That means that we couldn't use the trained model in order to predict new instances of the universe, which was a bit sad because this algorithm is very cool because behind the scene is the only one that runs graphics. This is really a graph model. So we end up with a different way of doing it. We said, okay, so we cannot use this for detecting population. What we can do, we can still reuse k-means, but not only k-means. We'll still try to have many features, one for each population or one for each genes in general. So what we've done, we've created, you can go to the notebook. So what we've done, we've created a k-means model that tries to find so many clusters, and we use these clusters as features for another model. So we use two different models in order to find where how this population is distributed along the samples. And this model was a random forest. If you want, you can take over if you like.
Yeah. So, as Andy mentioned, we want to be able to predict whether a genome is coming from a given population. Okay? It's something that people do because actually it tells us about our ancestry, the history of migrations, migration in the long history of humans, I mean. So this is something that scientists do. And so, again, the first thing is to prepare the data. As usual, it takes 90% of your time. And we prepare the data so that it fits the k-means machine, the k-means training function of MLlib. So we create actually an RDD, so a distributed data set, and each item is a vector containing the different genotypes. Okay? And then the first thing we do before starting the procedure is to separate a training set, which is 70% of the data, from a test set that we will use to validate the quality of our model. Okay? And we do that before anything else is undertaken.
Yeah.
Okay. So the first step, so imagine you have, actually in this data set we have more than 100,000 genotypes per individual. So that's really many features. And we want to use random forest to do that. And the principle with random forest is that you pick a feature, you see if this feature is able to separate into the different classes, and then you do that with another feature, picking it at random. But if you want to explore this space of 100,000 with such a procedure, you will need a huge tree that is not realistic to use. So what we want to do is reduce the number of features. We want to summarize all this data into something more compact, and that's why we use k-means. The argument is that, okay, we have all these individuals, we should be able to find in some way groups of them, okay, whatever it means, and then use the information of a given individual, how far he is from each of these center groups, and use this information as the input for the random forest, because it's easier to pick from 25 items in a uniform way than from 100,000, at least to cover the space, let's say. So we just train.
Yeah, we did it. I've shown it already.
Okay, so you've seen the training of the k-means, and the idea then is to measure the distance from each of these points to these centers, and this is our new data set that is derived from the training set only. And then, okay,
both. Yeah.
There we go. And then we run the random forest algorithms. And the random forest actually consists in having this decision tree where you split the data set given decision, how far is it from this item, then I separate into these two groups, and then I take this subgroup and I see how far is it from this other center, and I split my group. So I'm actually creating a kind of map of the space, chunking it into small regions and pointing each region to a certain class. Okay? And why forest? Because you take many of these decision trees and you kind of average the decision that is made from each of these forests. So it looks a bit like the procedure we've seen before, where you have to resample a number of times your data set to create different models and then average everything to get something that is more realistic given what you see of the universe. Okay.
So, right? Yeah, you train it.
Yeah, so it's
all the time, just a quick note, is that all the time the training or whatever we call from MLlib takes 2 lines. It's always the preparation of the data, the cleaning and all these stuff that takes so many lines. But in a sense that also shows that actually machine learning is not the hard part generally, is to find the right features or find the right way to represent your data. Just to say, okay, random forest takes 2 lines, actually it's one big line, by the way.
So then we make the prediction, and again, it's a very simple procedure, and we make this prediction on the test set, okay? So now we have a model and want to see what it gives on the test set, assuming that the test set that we have not optimized our model on represents correctly the entire universe, okay? Which is kind of far-stretched, but we have no choice. Okay. And then we compute confusion matrix. We see how many times an assigned class corresponds to the right one, and we see that it's pretty much diagonal. We have only 3 items that are misclassified in the test set, and the test set was not used to optimize the model. So it works pretty well.
Okay. Yeah, it's pretty interesting because finally we had a space that has 100,000 dimensions. Imagine the space that we have, and we have only 200 points there. And he was able to group those points into packages, 3 packages only. That's amazing, finally, just with a bunch of equations and very few lines of Scala, finally. So that's for a training set. For training set, of course, it's even better. We have more data and we have less misclassification. Sorry. Right.
Okay. Usually we measure what happens on the training set just to see if something converges, because it's no way testing on a test set if you didn't model your training set, right?
Right. So maybe some words. So we covered okay, what is machine learning? In a sense, basics. How a machine learning process is conducted from the data with a certain idea of a goal. Here it was certification. So that's what we just covered. But now that we've seen these things, we can say a word of what we expect to be the very hot topics in the next 5 to 10 years. The first thing is, of course, streaming. So this is a very hot topic in general. In engineering, we have all these devices that are coming with events, with information, and we would like to predict failures or whatever. And actually, most of the models are not done for that. They are not very prepared for that. That means that we have a lot of tricks in order to cope with this fact that new data are coming with new variants, maybe new context, new informations. So the information is very sparse. And also, we will need some architecture that are not really prepared as well. So, like having feedback systems, like this Lambda architecture, which is one of those architectures. But even in machine learning, you need this kind of architecture in order to take a model that is run in batch mode and it's injected into the streaming part of the prediction, right? So, because Spark is stateless. Huh? So you cannot really update the model while it's running. So you need something in order to be able to do it using this Lambda.
And the next thing that we are really looking at with a lot of attention and interest is the topic of probabilistic programming. Probabilistic programming is a field that aims at learning probabilistic models using programming languages. This means that it gives you really a lot of flexibility. You can do anything you want with a programming language, okay? So you can build really complex relationship between variables. And the interest of this probabilistic approach is that you're not only learning which features are important to predict something, but you learn also which relationship between those features are important. And this really gets closer to reasoning, to causality, and those kind of things. You do machine learning, usually it's because someone wants to make a decision on something he doesn't know. But that guy is in charge, he's responsible for his decision, so it's better that he's able to learn something, right? And this approach, this probabilistic approach is certainly a way to get more from the data than just an output. It's learning about the system itself, and it's something that is very important with the distributed computing frameworks, because those are quite hard problems. Usually you have to learn graph structures from the data that are inferred from the relationship between variables, so it's pretty NP-complete problems, let's say, and it requires a lot of data. But the technologies will allow in the near future to do really some exciting stuff with that.
Yeah. That's why we imported the Figaro library in our notebooks, because we are really playing with that. And Figaro is one of those programming languages that aims to bring progressive models to progressing languages, sorry, to other languages. So yeah, so we reached the end, finally. Notebooks were running quite well, only the machine was slow. But yeah, that's all, folks. I guess it's time for some questions and maybe some answers. Or we can run for beers. So we prepared. I'd rather go for beers. Close this one.